Hello, friend. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. Look up. Do you see that faint point of light trembling against the dark? It left its home 1,000 years ago, before your great-great-grandparents whispered their first words, before the oldest tree in your neighborhood broke through the soil. That light has been traveling toward you alone, through the cold and the quiet, just to meet your eyes tonight. But here's what makes you pause: that star might already be gone, dead, scattered. What you're seeing isn't a star at all. It's a ghost, a memory written in light, still traveling after the ending has already come. What if you've been looking at ghosts all your life? Before we begin, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's drift. Tonight we are going to watch stars live and die, but not the way you might think, not with distance or detachment. We're going to feel it the way a cloud of gas collapses into light, the way a giant runs out of fuel and tears itself apart, the way something dies and becomes the seed of something new. We'll move slowly through the life of a star, from birth in darkness to death in brilliance to rebirth in silence. You don't need to understand everything. Just rest and let curiosity do the listening. Stars are often called eternal, unchanging, fixed. Ancient cultures built calendars and myths around their stillness, their reliability, their quiet promise to always be there. The Egyptians used Sirius to predict the flooding of the Nile. The Polynesians crossed thousands of miles of open ocean, using only starlight as their guide. For most of human history, stars were the one thing we could trust not to change. But they do change. They live, they age, they die. It just happens so slowly that a single human lifetime is barely a blink in the star's long dream. If you could watch the sky the way a mountain watches the world, patient, silent, remembering everything you'd see, stars flicker on like candles in the dark, burn steady for billions of years, then collapse or explode or fade into something strange and small and dense. You'd see the whole sky shifting, breathing, evolving. The stars you see tonight are not the stars your ancestors saw. Not really. Some have grown brighter, some have dimmed. A few have vanished entirely. And in the places where there was only darkness before, new lights have appeared. Young stars just born beginning their long, slow burn. Stars are phoenixes. They die, and in dying they seed the clouds that will birth the next generation. Every atom in your body heavier than hydrogen, the carbon in your bones, the iron in your blood, the calcium in your teeth, was forged inside a star that died before the sun was born. You are made of star death. We all are. Scientists sometimes call this stellar nucleosynthesis. It's the process by which stars fuse lighter elements into heavier ones, creating the building blocks of planets, oceans, and people. But the phrase feels too clinical for what it really means: that you and I, and everyone we've ever loved, are walking, breathing monuments to stars that lived and died and gave themselves away. The astronomer Carl Sagan said it best in 1980. We are made of star stuff. Not metaphorically, literally. The atoms in your left hand likely came from a different star than the atoms in your right. You are a mixture of ancient explosions stitched together by gravity and time. It's strange to think about, isn't it, that something so distant, so vast, so seemingly separate from your life, could be the reason you exist at all. That the light you see when you look up is also the matter you're made of. That the universe isn't something you're in, it's something you are. Tonight we'll trace that journey, not as a lecture, not as a list. Just as a story told gently the way the night itself would tell it. We'll begin where all stars begin, in the dark. Long before there is light, there is only cloud. Cold. Dense. Mostly hydrogen with a trace of helium, and a whisper of heavier elements left behind by older stars. These clouds are called molecular clouds, and they drift through the galaxy like fog drifts through valleys, slow, silent, invisible to the naked eye. For millions of years, nothing happens. The cloud just floats. Gravity pulls at it, but weakly, and the gas pushes back with its own internal pressure. It's a balance, stable, boring even. But then something changes. Maybe a nearby star explodes, sending a shockwave rippling through the galaxy. Maybe two clouds collide. Maybe the cloud just drifts into a region where gravity is a little bit stronger. Whatever the reason, the balance tips, and the cloud begins to collapse. It happens slowly at first. Atoms drift inward, pulled by their own collective gravity. The cloud grows denser. As it does, it begins to fragment, breaking into smaller clumps, each one a future star, or a failed star, or a companion in a binary system. Each clump is called a Bok globule, named after the astronomer Bart Bok, who first studied them in the 1940s. They look like dark thumbprints against the glow of the Milky Way. Small, round, opaque, like shadows carved into light. Inside one of these globules, something extraordinary is happening. As the gas collapses inward, it heats up. Not because of any fire or chemical reaction, but simply because gravity is squeezing it, compressing it, forcing the atoms closer together. This is the same reason a bicycle pump gets warm when you use it. Compression generates heat. The temperature rises. 10 Kelvin, 100, 1,000, 10,000. The center of the collapsing cloud begins to glow faintly at first, then brighter. But you wouldn't see it, not yet. Because the cloud is still thick with dust and gas, and the light is trapped inside, hidden from the universe. This is a protostar, not quite a star. Not yet. Just a dense, hot core pulling in more and more material, growing heavier and hotter with every passing century. Protostars were invisible to us for most of human history. They hide inside their birth clouds, shrouded in dust that absorbs visible light and re-emits it as infrared radiation heat we couldn't detect until the 20th century. It wasn't until the 1980s, with the launch of the infrared astronomical satellite, that we could finally peer inside stellar nurseries and see the protostars glowing in the dark. What we found was astonishing. In the Orion Nebula alone, one of the closest star-forming regions to Earth, just 350 light-years away, there are hundreds of protostars in various stages of formation. Some are barely warm, others are nearly ready to ignite. The Hubble Space Telescope has captured images of these objects, and they look like glowing seeds buried in cotton or embers hidden in ash. One of the most famous examples is a region called the Pillars of Creation, located in the Eagle Nebula about 6,500 light-years from Earth. The name is poetic but accurate. These towering columns of gas and dust are actively forming new stars. In 1995, the Hubble Space Telescope photographed them, and the image became one of the most iconic in the history of astronomy. The pillars are enormous. Each one is several light-years long, and at their tips you can see dense knots where protostars are beginning to form. In 2022, the James Webb Space Telescope looked at the Pillars of Creation again, this time in infrared. What it revealed was breathtaking dozens of newborn stars, glowing red and orange hidden inside the pillars. Stars that Hubble couldn't see. Stars that were there all along, waiting to be witnessed. It takes time for a protostar to become a star. Millions of years. During this long childhood, the protostar continues to pull in gas and dust from the surrounding cloud. As it does, it spins faster. Conservation of angular momentum, the same principle that makes a figure skater spin faster when they pull their arms in. The spinning material forms a disk around the protostar, and from this disk, planets may eventually form. But first, the star itself must be born. Deep in the core, the temperature continues to rise. 1 million Kelvin, 5 million, 10 million. At around 15 million Kelvin, something miraculous happens. Hydrogen nuclei protons begin to collide with enough energy to overcome their natural repulsion. Remember, Protons are positively charged, and like charges repel each other. Under normal circumstances, they would never touch. But at 15 million Kelvin, moving at thousands of kilometers per second, some of them collide so violently that they fuse together. Two protons become one helium nucleus. And in the process, a tiny amount of mass is converted into energy. Einstein's equation, E, or mc2, tells us that even a small amount of mass contains a staggering amount of energy. When you fuse hydrogen into helium, about 0.7% of the mass is lost, transformed into light heat and pressure. This is nuclear fusion. This is the moment a star is born. The protostar is now a star. And for the first time in its life, it fights back against gravity. The energy released by fusion creates an outward pressure radiation, pressure that balances the inward pull of gravity. The star reaches what astronomers call hydrostatic equilibrium, a delicate, perfect balance between collapse and explosion. It will stay in this balance for most of its life, and that life can be very, very long, or surprisingly short. It all depends on one thing: mass. A star's mass determines everything: how hot it burns, how bright it shines, how long it lives, even how it dies. If a collapsing cloud doesn't gather enough mass, less than about 0.08 times the mass of our sun, it will never get hot enough to fuse hydrogen. It will glow dimly for a while, radiating away its leftover heat, then fade into darkness. These objects are called brown dwarfs, and they occupy a strange space between planets and stars. The first confirmed brown dwarf, Gliese 229b, was discovered in 1995, about 19 light-years from Earth. It glows faintly in infrared, a failed star that never quite made it. But if the cloud gathers just a little more mass, 0.08 solar masses, or more fusion ignites, the star is born. And from that moment on, its fate is written. Low-mass stars, like red dwarfs, burn slowly and steadily. They're small, cool, and dim, but they're incredibly efficient. A red dwarf can live for trillions of years longer than the current age of the universe. Proxima Centauri. The closest star to our sun is a red dwarf. It formed about 485 billion years ago, and it will still be shining long after our sun has died. Medium-mass stars like our sun burn hotter and brighter, but they don't last as long. The sun has been fusing hydrogen for about 4.6 billion years, and it has roughly another 5 billion years to go. Not a short life by human standards, but not eternal either. And massive stars, giants, dozens or even hundreds of times more massive than the sun, burn ferociously. They're bright, hot, and profligate, consuming their fuel at a reckless pace. A star like Eta Carinae, one of the most massive stars known, will live for only a few million years. It's already middle-aged, and it could explode at any time. Why do massive stars die so young? Because the more massive a star is, the hotter its core must be to support its own weight. And the hotter the core, the faster fusion occurs. It's a cruel irony the biggest stars are also the most short-lived. Our sun sits comfortably in the middle, not too big, not too small, just right. Ordinary in the best possible way. This ordinariness is part of what makes life on Earth possible. If the sun were much larger, it would have burned out long before complex life could evolve. If it were much smaller, Earth would be too cold, locked in a frozen orbit around a dim red star. But the sun is neither. It's a G-type main sequence star, yellow and steady burning, at a temperature of about 5,500 degrees Celsius on its surface and 15 million degrees at its core. It's been stable for billions of years, and it will remain stable for billions more until it doesn't. But we'll get to that. For now, let's just sit with this, the moment of ignition. The moment when a cloud of cold hydrogen becomes something new, something radiant, something alive in its own way. There's a word astronomers use for this phase of a star's life just before fusion fully stabilizes. They call them T Tauri stars, named after the first one discovered in the constellation Taurus. T-Tauri stars are young less than 10 million years old, and they're chaotic. They flare unpredictably. They spin rapidly. They blast powerful stellar winds into space, clearing away the leftover gas and dust from their birth clouds. Our sun was once a T-Tauri star. 4.5 billion years ago, it was wild, unstable, still figuring out how to be a star. And around it, in the swirling disk of gas and dust, the planets were beginning to form. Earth was just a collection of rocks smashing together in the dark. It's humbling, isn't it? To think that everything we know, every ocean, every mountain, every city, every person, began as debris orbiting a young, violent star. And here's the thing, it's still happening. Right now. All across the galaxy in clouds like Orion and the Eagle Nebula and thousands of other stars are being born. Some will be small and dim, living quietly for trillions of years. Some will be massive and bright, burning out in a cosmic instant. And some will be just like the sun, ordinary, patient, steady. And maybe orbiting one of those stars on a rocky planet in just the right orbit, something will look up at its sky and wonder. What happens next is a long, slow burn, a period of stability, a time when the star simply exists, steady, reliable, unchanging at least on the surface. We call this phase the main sequence, and it's where stars spend most of their lives. Before there is light, there must be darkness. Before there is a star, there must be a cloud. Cold, dense, invisible to the eye, but full of potential. Full of hydrogen, helium, and a trace of heavier elements left behind by stars that died before this cloud even existed. These are the stellar nurseries, molecular clouds. And they are where every star begins. Right now, scattered throughout the Milky Way, there are regions where stars are being born. Not one star at a time, but dozens, hundreds, sometimes thousands, all from the same collapsing cloud. And if you could see them, really see them in infrared or radio wavelengths, you'd witness one of the most beautiful processes in the universe, the birth of light from darkness. Molecular clouds are vast, truly vast. Some of them stretch for hundreds of light years, containing enough mass to form tens of thousands of stars. And yet, for millions of years, they just float, drifting through the galaxy. Cold, dark, mostly hydrogen with temperatures hovering around 10 to 20 Kelvin. That's minus 260 degrees Celsius, just a few degrees above absolute zero. At these temperatures, atoms barely move. The cloud is stable, held in a delicate balance between its own gravity trying to pull it together and internal pressure pushing outward. It's a stalemate. Nothing happens until something breaks the balance. Maybe a nearby star explodes as a supernova, sending a shock wave rippling through the galaxy. Maybe two molecular clouds collide in the crowded disk of the Milky Way. Maybe the cloud just drifts into a region where the gravitational pull is slightly stronger, perhaps near a spiral arm, where matter is more densely packed. Whatever the trigger, the result is the same. The cloud begins to collapse. Gravity, patient and relentless, starts to win, slowly at first. Atoms drift inward, pulled by their collective mass. The cloud grows denser, and as it does, something remarkable happens. It fragments. The cloud doesn't collapse as one uniform mass. Instead, it breaks into smaller clumps, each one dense enough to collapse independently. These clumps are called Bok globules, named after the Dutch-American astronomer Bart Bok, who studied them extensively in the 1940s. Bok globules are small by cosmic standards, typically a few light years across, containing maybe 10 to 50 times the mass of the sun. But they're incredibly dense compared to the surrounding cloud. And they're dark, opaque, so thick with dust that no visible light can penetrate them. For decades, astronomers could only see Bok globules as dark silhouettes against brighter backgrounds, shadows against the glow of distant stars or nebulae. They looked like holes in space voids where starlight couldn't reach. But they're not voids, they're wombs. Inside each Bach globule, something is happening. The collapse continues. The center of the globule grows hotter as gravity compresses the gas. Atoms collide more frequently. Kinetic energy is converted to heat. This is a fundamental principle of physics. When you compress a gas, it heats up. It's the same reason a bicycle pump gets warm. When you use it, the same reason the Earth's core is hot, despite being solid metal. Compression generates heat. And in the center of a collapsing Bach globule, the temperature begins to rise. 10 Kelvin becomes 100. 100 becomes 1,000. 1,000 becomes 10,000. The gas starts to glow faintly at first in the infrared. This is a protostar, not yet a star, not yet capable of fusion, but a hot, dense core pulling in more and more material from the surrounding globule, growing heavier with every passing year. The problem for astronomers is that protostars are invisible in optical light. The surrounding dust absorbs all the visible photons. What little light escapes is in the infrared heat radiation. For most of human history, we couldn't see inside stellar nurseries. We knew stars had to form somehow, but the process was hidden from us, shrouded in dust. That changed in the 1980s with the launch of the Infrared Astronomical Satellite, or IRAS. For the first time, we could peer through the dust and see the protostars glowing inside. And what we found was astonishing. One of the most famous stellar nurseries is the Orion Nebula, located about warm 350 light-years from Earth. It's visible to the naked eye as a fuzzy patch in Orion's sword just below the 3 stars of Orion's belt. But what you see with your eyes is only a fraction of what's really there. When you look at the Orion Nebula in infrared, the whole region lights up. Hundreds of protostars hidden in the visible light images suddenly become visible. Some are just beginning to form. Others are nearly ready to ignite fusion in their cores. The Orion Nebula is a stellar factory churning out new stars at a prodigious rate. It's only about 2 million years old, a newborn by cosmic standards, but it's already produced a cluster of hot young stars called the trapezium, which illuminate the surrounding gas and make the nebula glow. These young stars are clearing away the remaining gas and dust, revealing the stellar nursery beneath. In another few million years, the nebula will disperse entirely, and all that will remain is an open cluster of stars drifting through the galaxy together. But the most iconic stellar nursery image isn't from Orion. It's from a nebula 6,500 light-years away in the constellation Serpens, the Pillars of Creation. You've probably seen this image. It's one of the most famous photographs ever taken by the Hubble Space Telescope. 3 towering columns of gas and dust, backlit by the glow of newborn stars stretching across light-years of space. The name is poetic, but it's also accurate. These are pillars of creation. At the tips of each column, dense knots of material are collapsing under their own gravity, forming new stars. The pillars themselves are being sculpted by the intense ultraviolet radiation from nearby hot stars, which is slowly eroding them like wind-carving sandstone. When Hubble captured this image in 1995, it became an instant icon. It's been reproduced on posters, t-shirts, stamps. It's appeared in textbooks, documentaries, museums. It represents more than any other image the idea that stars are born. But here's something most people don't know. The pillars of creation might already be gone. In 2007, infrared observations from the Spitzer Space Telescope detected a shock wave from a nearby supernova that had passed through the region about 6,000 years ago. That shock wave likely destroyed the pillars, but because the pillars are 6,500 light-years away, we won't see that destruction for another 500 years. Right now in our sky, the pillars still stand, but they're already a memory, an image of something that no longer exists. It's a reminder that when we look at the stars, we're not seeing the universe as it is. We're seeing it as it was. Light takes time to travel, and the farther away something is, the farther back in time we're looking. In 2022, The James Webb Space Telescope, Hubble's successor, with far more powerful infrared capabilities, turned its gaze toward the pillars of creation. What it revealed was breathtaking. Where Hubble saw the pillars as opaque columns, Webb saw through them. Inside the dust, hidden from Hubble's view, were dozens of protostars glowing red and orange in the infrared. Stars that had been invisible before, suddenly revealed. It was like turning on a light in a dark room. All along the pillars had been full of stars in the process of forming, and we just couldn't see them. Webb's image showed something else too. At the very tips of the pillars, where the densest knots of material are located, the protostars are the brightest. These are the youngest stars, still actively pulling in gas and dust from their surroundings still growing. And surrounding each protostar is a disk. A protoplanetary disk. The same kind of disk that once surrounded our sun 4.6 billion years ago and from which the planets formed. These disks are where planetary systems are born, and seeing them in such detail in so many different stellar nurseries has taught us something profound. Planet formation is not rare, it's common, perhaps even inevitable. Almost every star we've observed in detail has a disk around it during its early life. And in many of those disks, we've seen gaps, clear spaces carved out by forming planets. We're not alone in having a planetary system. The galaxy is full of them. But let's return to the protostar itself, hidden inside its cocoon of gas and dust, growing hotter and denser with every passing millennium. For a protostar, the journey from cold cloud to nuclear furnace takes a long time, a very long time. Roughly 50 million years on average for a sun-like star. During this time, the protostar is pulling in material from the surrounding disk at a rate of about 1/millionth to 100,000th of a solar mass per year. It doesn't sound like much, but over millions of years it adds up. And as the protostar grows more massive, its core grows hotter. The pressure increases, the density increases, the temperature climbs higher and higher. 1 million Kelvin, 5 million, 10 million. And then, at around 15 million Kelvin, something miraculous happens. Two hydrogen nuclei protons collide with enough energy to overcome the electromagnetic force that normally keeps them apart. They fuse. They become helium. And in the process, they release energy. Nuclear fusion has begun. The protostar is now a star. But it's not a smooth transition. The first fusion reactions are sporadic, uneven. The star is still figuring out how to balance the inward pull of gravity with the outward push of radiation pressure. This phase is called the T Tauri phase, named after the first star of this type, discovered T Tauri in the constellation Taurus. T Tauri stars are young, typically less than 10 million years old, and they're chaotic. They flare unpredictably. They spin rapidly. They emit powerful stellar winds that blast away the remaining gas and dust in the protoplanetary disk, clearing the way for planets to form. Our sun was once a T Tauri star. About 4.6 billion years ago, it was wild, unstable, still settling into the stable fusion and cycle that would sustain it for the next 10 billion years. And around it, in the swirling disk of gas and dust, small grains were beginning to stick together. Dust became pebbles. Pebbles became boulders. Boulders became planetesimals. And planetesimals collided and merged, growing into protoplanets. It was a violent process. Collisions were constant. The early solar system was a chaotic mess of debris, with objects smashing into each other at thousands of kilometers per hour. But slowly, over tens of millions of years, order emerged. The planets found stable orbits. The leftover debris was either swept up or ejected. And the sun settled onto the main sequence, burning hydrogen steadily, reliably for the first time. Here's something worth thinking about. The sun you see in the sky today is not the same sun that illuminated the early Earth. It's 30% brighter now than it was 4.6 billion years ago, and it will continue to brighten gradually over the next few billion years. This slow brightening is one of the great challenges for life on Earth. As the sun gets brighter, Earth receives more energy. The climate warms. Eventually, in about 1 billion years, maybe sooner, the oceans will begin to evaporate. The runaway greenhouse effect will set in. Earth will become uninhabitable. But that's still a long way off. For now, the sun is stable, and stars like the sun scattered throughout the galaxy are providing steady energy to countless worlds, some of which perhaps are home to life. Stellar nurseries are not static, they're constantly evolving. Stars are born, grow, and begin to clear away the gas and dust that once hid them. And as they do, they trigger new waves of star formation in neighboring regions. The radiation and stellar winds from hot young stars compress nearby clouds, causing them to collapse and form new stars. It's a cascade, a chain reaction, one generation of stars giving rise to the next. And each new generation is slightly different, slightly richer in heavy elements, because some of the first stars have already died, exploding as supernovae, scattering their ashes into the interstellar medium. Those ashes, carbon, oxygen, iron, silicon, mix with the primordial hydrogen and helium, enriching the next generation of molecular clouds. And from those enriched clouds, new stars form, stars with planets, stars that might host life. We are the result of this process. The sun formed from a cloud that had already been enriched by earlier generations of stars. The Earth contains elements that didn't exist in the early universe. Elements that had to be created inside stars through fusion and then released through stellar death. Every atom of carbon in your body was forged in the core of a red giant. Every atom of iron in your blood was created in a supernova explosion. You are made of stardust, literally. And somewhere right now, in a cold, dark molecular cloud, another star is beginning its journey. Collapsing, heating, pulling in material, preparing for that first moment of fusion. Another star, perhaps, with planets, perhaps, with worlds where something will one day look up and wonder as we do where it all began. The nursery is never empty. The cycle never stops. Darkness becomes light. And light eventually returns to darkness, only to become light again. But once a star ignites, once fusion begins in the core, something profound happens. The star reaches a balance, gravity pulling inward, radiation pushing outward. And in that perfect equilibrium, the star can burn for billions of years, steady and unchanging. This is the main sequence, and it's where most stars spend most of their lives. There's a moment in every star's life that changes everything, a single instant when the waiting ends and the burning begins, when cold becomes hot, when darkness becomes light, when a cloud of hydrogen falling inward for millions of years suddenly pushes back. This is ignition, and it happens only once. The temperature at the core has been climbing slowly, steadily for what feels like forever in human terms, but is merely a breath in cosmic time. 10 million Kelvin, 12 million, 14 million. The hydrogen nuclei are moving faster now, colliding more frequently, but still they bounce apart. The electromagnetic force, the repulsion between positive charges, keeps them separate. But then, at around 15 million Kelvin, something shifts. A few hydrogen nuclei collide with so much energy that they overcome the repulsion. They touch, they merge. Two protons fuse into a single helium nucleus, releasing a burst of energy in the process, energy in the form of gamma rays, neutrinos, and heat. It's a tiny event, barely noticeable really in the grand scheme of things. One fusion reaction among trillions upon trillions. But it's enough, because that energy heats the surrounding gas, which increases the collision rate, which creates more fusion, which releases more energy, which heats more gas. It's a chain reaction, a runaway process. Within moments, cosmically speaking, the core is ablaze with fusion reactions and the protostar becomes a star. The outward pressure from fusion now balances the inward pull of gravity. The star reaches hydrostatic equilibrium, and for the first time in its existence, it stabilizes. This moment, this ignition, was predicted theoretically long before we understood it in detail. In 1920, the British astrophysicist Arthur Eddington proposed that stars must be powered by some kind of subatomic process, something far more efficient than chemical burning. He was right, but he didn't know the mechanism. It wasn't until 1939 that the German-American physicist Hans Bethe figured it out. He described the proton-proton chain, the series of nuclear reactions that fuse hydrogen into helium in stars like our Sun. For this work, Bethe won the Nobel Prize in Physics in 1967. He gave us the answer to one of humanity's oldest questions: what makes the sun shine? The answer is both simple and profound. The sun shines because it is destroying itself. Every second it converts about 600 million tons of hydrogen into helium. In the process, about 4 million tons of matter, pure mass, is converted into energy, according to Einstein's famous equation E=mc2. That energy radiates outward, taking thousands of years to travel from the core to the surface, then just 8 minutes to reach Earth. And when it does, it warms your skin, grows your food, powers your civilization. You are alive because a star is dying slowly at a rate of 4 million tons per second. But let's step back for a moment. Because not all stars ignite the same way. The process depends entirely on mass. If a collapsing cloud gathers less than about 0.08 times the mass of the Sun, roughly 80 times the mass of Jupiter, it will never achieve the core temperature necessary for hydrogen fusion. The core will heat up, yes. It may even glow faintly for a while, but it will never truly ignite. These failed stars are called brown dwarfs. They're not quite stars, not quite planets. They exist in a twilight category objects that almost made it but didn't gather quite enough mass. They radiate mostly in the infrared, invisible to the naked eye. For a long time, astronomers weren't sure brown dwarfs even existed. They were predicted theoretically in the 1960s, but it wasn't until 1995 that the first one was confirmed. It was called Gliese 229b. And it orbits a red dwarf star about 19 light-years from Earth. When astronomers analyzed its spectrum, they found methane, a molecule that can only exist at relatively low temperatures. This was the smoking gun. A true star would be too hot for methane to survive. Gliese 229b was something else, something in between. Since then, thousands of brown dwarfs have been discovered, each one a reminder that the universe is full of almosts, objects that tried to become stars but fell just short. But if a cloud gathers just a little more, mass 0.08 solar masses or above, fusion ignites. The star is born. And from that moment, its entire future is determined by how much mass it managed to collect. This is the fundamental rule of stellar life: mass is destiny. A low-mass star, say 1 to 0.5 times the mass of the Sun, will burn its hydrogen slowly and carefully, like a candle that refuses to go out. These are red dwarfs, the most common stars in the galaxy. They're small, cool, and dim, often invisible without a telescope, but they're efficient. A red dwarf can live for trillions of years, far longer than the current age of the universe. Proxima Centauri, the closest star to our Sun, at just 4.24 light-years away, is a red dwarf. It's been burning for about 485 billion years, roughly as long as the Sun, but it will continue burning for another 4 trillion years. When the Sun has long since died, when the Milky Way has collided with Andromeda and formed a new galaxy, when the last of the massive stars have exploded and faded, Proxima Centauri will still be there, glowing faintly in the dark. There's something both comforting and unsettling about that isn't there. That a star so small, so dim, so unremarkable will outlast everything else. On the other end of the spectrum are the massive stars. Stars with 10, 20, 50, even 100 times the mass of the Sun. These are the giants, the supergiants, the hypergiants. They burn hot and bright and fast. Eta Carinae, one of the most massive stars known, is a good example. It's located about 7,500 light-years away in the constellation Carina, and it's a monster. Estimates suggest it's between 100 and 150 times the mass of the Sun, and it shines with the brightness of 5 million suns. It's so luminous that if you replace the Sun with Eta Carinae, Earth would be vaporized instantly. But here's the catch: Eta Carinae has only been burning for about 3 million years, and it's already nearing the end of its life. It could explode as a supernova tomorrow or in 100,000 years. On cosmic timescales, those are the same thing. Why do massive stars live such short lives? It seems counterintuitive, doesn't it? You'd think that more fuel would mean a longer life. But the opposite is true. The reason has to do with the relationship between mass gravity and fusion rate. A massive star has more hydrogen to burn, yes, but it also has much stronger gravity pulling inward. To balance that gravity, the core must generate more outward pressure, which means it must fuse hydrogen much faster. And the faster it burns, the sooner it runs out. It's like comparing a small campfire to a bonfire. The campfire might burn all night. The bonfire might be 10 times larger, but it will burn out in an hour. Mass is destiny. And for massive stars, destiny arrives quickly. Our Sun sits comfortably in the middle of this spectrum. It's a G-type main sequence star, neither too large nor too small, with a surface temperature of about 500 degrees Celsius and a core temperature of 15 million Kelvin. It's been fusing hydrogen for about 4.6 billion years, and it has roughly another 5 billion years to go before it exhausts its core fuel. In astronomical terms, the Sun is utterly ordinary. There's nothing special about it. It's one of hundreds of billions of similar stars in the Milky Way alone. But that ordinariness is, in a strange way, what makes it extraordinary. Because if the Sun were just a little bit different, a little more massive, a little less massive, life on Earth might never have evolved. If the Sun were a red dwarf, Earth would need to orbit much closer to receive enough warmth. But close orbits around red dwarfs are dangerous. These stars are prone to violent flares, sudden bursts of radiation that could strip away a planet's atmosphere. And because red dwarfs are so dim, a planet in the habitable zone would likely become tidally locked, with one side always facing the star and the other locked in eternal night. If the Sun were a massive star, it would burn out long before complex life could evolve. It takes billions of years for single-celled organisms to become multicellular, for fish to crawl onto land, for intelligence to emerge. A massive star doesn't give you billions of years. It gives you millions maybe, and then it explodes. The Sun gives Earth time, stability, patience. And in return, Earth gives rise to oceans, forests, cities, and minds that can look up and wonder. There's a term astronomers use for the moment when a star reaches hydrostatic equilibrium and settles into a stable fusion cycle. They say the star has arrived on the main sequence. It's a strange phrase if you think about it, as if the star is stepping onto a platform, taking its place among billions of others. But in a way, that's exactly what's happening. The main sequence is not a place, it's a phase. A long, stable period during which the star fuses hydrogen into helium in its core, balancing gravity, with radiation pressure shining steadily for millions, billions, or trillions of years. Most stars spend about 90% of their lives on the main sequence. It's the longest chapter in their story, the quiet middle, the time when nothing dramatic happens. But just because it's stable doesn't mean it's simple. Even on the main sequence, stars are extraordinarily dynamic. The Sun, for instance, is constantly churning. Hot plasma rises from the core toward the surface, cools, and sinks back down in massive convection currents. The surface is covered in sunspots, regions where magnetic fields suppress convection, creating cooler, darker patches. And every so often, those magnetic fields become twisted and unstable, releasing bursts of energy called solar flares and coronal mass ejections, events that can disrupt satellites, power grids, and communication systems here on Earth. In 1859, one of the most powerful solar flares ever recorded struck Earth. It was called the Carrington event, named after the British astronomer Richard Carrington, who observed the flare through his telescope. The resulting geomagnetic storm was so intense that telegraph systems around the world sparked and caught fire. Operators reported receiving electric shocks. Auroras typically confined to polar regions were seen as far south as the Caribbean. If a Carrington-level event happened today, the damage would be catastrophic. Our modern infrastructure, satellites, GPS, the internet power grids, is far more vulnerable than 19th century telegraph wires. The sun is stable, yes, but it's not tame. And yet, compared to some stars, the sun is remarkably well behaved. Young stars, those still in their T-Tauri phase, not quite settled onto the main sequence, are chaotic and unpredictable. They flare constantly, sometimes increasing in brightness by several magnitudes in a matter of hours. They spin rapidly, completing a full rotation in just a few days compared to the sun's 25-day rotation period. And they blast powerful stellar winds into space, clearing away the leftover gas and dust from their birth clouds. Our sun was once like this. 4.5 billion years ago, it was a T-Tauri star, wild, unstable, still learning how to be a star. Around it in the protoplanetary disk, the planets were beginning to form. Rocky planets, close and gas giants farther out, each one coalescing from the debris of the solar nebula. The young sun's powerful winds helped shape the solar system. They blew away the lighter elements, hydrogen and helium, from the inner regions, leaving behind only the heavier materials like rock and metal. That's why the inner planets, Mercury, Venus, Earth, Mars, are small and rocky, while the outer planets, Jupiter, Saturn, Uranus, Neptune, are massive and gaseous. Without that stellar wind, Earth might have ended up as a gas giant, or it might not have formed at all. It's remarkable really how many small accidents and coincidences had to align for us to be here. The sun had to be the right mass. It had to form in the right part of the galaxy. It had to settle onto the main sequence at just the right time. And Earth had to form in just the right orbit with just the right composition, just the right atmosphere. One thing different, and we wouldn't be here to wonder about it. But here's what keeps me up at night, in the best way this process is still happening. Right now, all across the galaxy, protostars are reaching ignition. Clouds are collapsing, cores are heating up. And somewhere, maybe on a planet orbiting a star, we'll never see something is beginning to wonder. There's a beautiful inevitability to it, don't you think? That given enough time, enough space enough, hydrogen stars will form. Planets will coalesce. And life's strange, curious, fragile life will find a way to look up and ask, what are we? Where do we come from? Why are we here? We don't have final answers to those questions. Maybe we never will, but we have the story of how stars are born, how they live, how they die. And in that story, we find ourselves, because we are not separate from the stars. We are part of them. We are what happens when a star's ashes gather together and start asking questions. There's one more thing worth mentioning about ignition, one more detail that makes the whole process feel even more miraculous. When fusion begins, it doesn't happen everywhere at once. It starts in the very center of the core, where the temperature and pressure are highest. But even there, it's rare. At any given moment, only a tiny fraction of the hydrogen nuclei in the sun's core are actually fusing. Most of them just collide and bounce apart. In fact, if you took a single hydrogen nucleus and placed it in the sun's core, it would take on average about 9 billion years before it fused with another nucleus. 9 billion years. That's longer than the sun has been alive. And yet the sun produces enough energy to light up the solar system because there are so many hydrogen nuclei in the core, roughly 10B or 56 of them, that even though each individual fusion is rare, the total number of fusions happening every second is staggering. About 10^-8 fusion reactions per second to be specific. That's a number so large it's almost meaningless. But here's a way to think about it. If you could count one fusion reaction per second, it would take you longer than the age of the universe to count just 1 second's worth of reactions in the sun. The sun is not one fire. It's trillions upon trillions of tiny fires all burning at once, all releasing energy that eventually finds its way to the surface and radiates out into space. And 8 minutes later, some of that energy reaches you. It's humbling, isn't it? That the light warming your face right now began as a fusion reaction deep inside the sun. Millions of years ago, fought its way to the surface through a dense maze of plasma and then traveled 93 million miles through the vacuum of space just to touch your skin. The universe is vast and cold and mostly empty. But every now and then, a photon arrives, and for a moment you feel connected to something larger. For now, the star burns, steady, patient, balanced between collapse and explosion. It has found its equilibrium, and it will hold that balance for as long as the fuel lasts. Stability in the cosmic sense is not stillness, it's balance. A constant push and pull, gravity and pressure locked in an endless negotiation. And for most of a star's life, that negotiation holds. This is the main sequence, the long middle. The quiet chapter, where nothing seems to happen and yet everything is happening constantly and visibly in the burning core, where hydrogen becomes helium and light is born. For our sun, this chapter has already lasted 4.6 billion years, and it will last another 5 billion more. It's hard to grasp that kind of time, isn't it? Harder still to imagine what it means for a star to simply exist, not growing, not shrinking, just burning steadily, one fusion reaction at a time, for longer than continents drift, longer than mountains rise and fall, longer than entire species evolve and disappear. And yet, that's what stars do. They wait, they endure, they outlast almost everything. The term main sequence itself comes from one of the most important diagrams in all of astronomy, the Hertzsprung-Russell diagram, or HR diagram for short. It was developed independently by two astronomers in the early 1910s, Einar Hertzsprung from Denmark and Henry Norris Russell from the United States. What they did was elegant in its simplicity. They took a large sample of stars and plotted them on a graph, luminosity on one axis, temperature on the other. And when they did, something remarkable appeared. The stars weren't scattered randomly. They formed patterns, distinct regions. Most stars, about 90% of them, clustered along a diagonal band running from the upper left, hot and bright, to the lower right, cool and dim. Hertzsprung and Russell called this band the main sequence, and they realized it represented stars in the prime of their lives, fusing hydrogen into helium in their cores. But there were other regions too. A cluster of stars in the upper right, cool but extremely luminous. These were the giants, and a small group in the lower left, hot but very dim. These were the white dwarfs, the remnants of dead stars. The HR diagram became a map of stellar life. You could look at a star's position and know immediately what stage it was and how long it had been burning, how long it had left. It's still used today over a century later. Every astronomy student learns to read it. Every stellar model is tested against it. It's one of those rare scientific tools that's both simple and profound. And what it tells us is this: the main sequence is not one thing, it's a spectrum. A range of possibilities, all determined by mass. At the cool end of the main sequence, you have the red dwarfs. Small stars barely massive enough to sustain fusion with surface temperatures around 2,500 to 4,000 Kelvin. They glow a dull red, often too dim to see without a telescope, even from just a few light years away. But they're survivors. A red dwarf with 0.1 solar masses will burn for an estimated 10 trillion years. That's about 700 times longer than the current age of the universe. Think about that. The universe is 13.8 billion years old. The first red dwarfs that formed in the early universe are still in their infancy. They haven't even begun to age. When the last massive stars have long since exploded, when the sun has cooled to a white dwarf, when galaxies have drifted so far apart that the night sky is nearly empty, those red dwarfs will still be burning, quietly, slowly, alone. There's something both beautiful and melancholy about. that isn't there. To be the last lights in a darkening universe. Proxima Centauri, our nearest stellar neighbor, is one of these red dwarfs. It's just 4.24 light-years away, close enough that in principle we could send a probe there within a human lifetime if we had the technology. And when we look at Proxima through a telescope, what we see is a star that's almost comically faint. If you replace the sun with Proxima Centauri, it would appear about as bright as a full moon. You could read by it maybe, but you'd need to be much closer to stay warm. And yet, Proxima Centauri will outlive the sun by a factor of hundreds. It will outlive every G-type star, every F-type star, every O and B-type star. It will be one of the last stars still burning when the universe grows cold and dark. On the other end of the main sequence, you have the blue giants, massive hot stars with surface temperatures of 10,000 to 50,000 Kelvin or more. They shine brilliant blue-white so bright they can be seen from thousands of light-years away. But they burn fast, recklessly, a star like Rigel in the constellation. Orion is about 20 times the mass of the sun and shines with the light of 120,000 suns. It's so luminous that if you replace the sun with Rigel, the heat would be intolerable even out at the orbit of Neptune. Earth would be vaporized instantly. Rigel has been burning for only about 8 million years, and it's already nearing the end of its main sequence life. Within another few million years, perhaps much sooner, it will exhaust its core hydrogen swell into a supergiant and eventually explode as a supernova. 8 million years sounds like a long time, but in cosmic terms, it's a flash, a blink. Barely enough time for the dust to settle after the star's birth. Why do massive stars die so young? It comes down to that same fundamental relationship we've mentioned before: mass gravity and fusion rate. A massive star has much stronger gravity pulling inward, which means it needs much more outward pressure to resist collapse. And to generate that pressure, the core must fuse hydrogen at a much higher rate. The more massive the star, the faster it burns. Not linearly, but exponentially. A star twice as massive as the sun doesn't burn twice as fast, it burns about 16 times as fast. A star 10 times as massive burns thousands of times as fast. It's a cruel trade-off. More fuel, yes, but burns so prodigiously that the extra supply doesn't help. The bonfire metaphor holds bigger doesn't mean longer. It means hotter, brighter, and faster to ash. Somewhere in the middle of all this, between the patient red dwarfs and the reckless blue giants, you find stars like the sun. G-type stars. Yellow dwarfs, ordinary in every sense. The sun is not the brightest star, not the hottest, not the longest lived, not the most massive. If you picked a star at random from the Milky Way, it would probably be smaller and dimmer than the sun. But the sun is comfortable, stable, right in the sweet spot for supporting life. Its surface temperature is about 500 degrees Celsius. Its core temperature is 15 million Kelvin. It converts roughly 600 million tons of hydrogen into helium every second, releasing enough energy to power the entire solar system. And it has been doing this steadily for 4.6 billion years. Here's what's astonishing. Over those 4.6 billion years, the sun has barely changed. It's about 30% brighter now than it was when it first settled onto the main sequence, a result of the helium accumulating in the core, which increases the core density and slightly raises the fusion rate. But 30% over 4.6 billion years is a glacial pace, slow enough that life on Earth had time to adapt to evolve to thrive. If the sun had been more variable, if it had brightened or dimmed by even 10% over the course of a few million years, complex life might never have taken hold. Ecosystems are fragile. They depend on predictable conditions, stable climates, steady energy input. The sun gave Earth that stability, and Earth in turn became a living world. There's a concept in astronomy called the habitable zone, sometimes poetically called the Goldilocks zone. It's the region around a star where conditions are just right for liquid water to exist on a planet's surface. Not too hot, not too cold, just right. For a star like the Sun, the habitable zone extends from about 0.95 to 1.4 astronomical units. That is from just inside Earth's orbit to just outside Mars's orbit. Earth sits almost perfectly in the middle, but the habitable zone depends on the star. Around a red dwarf, the zone is much closer in because the star is cooler. Around a blue giant, the zone is farther out because the star is hotter. And in both cases, there are complications. For red dwarfs, the habitable zone is so close that planets are likely to become tidally locked, one side always facing the star, the other locked in eternal darkness. Imagine a world where one hemisphere is scorched by perpetual daylight, while the other freezes in permanent night. Life could exist maybe in the narrow twilight band between the two extremes, but it would be strange alien nothing like what we know. And red dwarfs are prone to flares, sudden violent bursts of radiation that could strip away a planet's atmosphere. Proxima Centauri, for instance, flares regularly, sometimes increasing in brightness by tenfold or more for a few minutes. Any planet in its habitable zone would be bathed in intense ultraviolet and X-ray radiation. For blue giants, the problem is time. Even if a planet formed in the habitable zone and had liquid water, the star wouldn't live long enough for complex life to evolve. It takes billions of years for single-celled organisms to become multicellular, for photosynthesis to develop, for intelligence to emerge. Blue giants give you millions of years at most. The Sun, on the other hand, gives you 10 billion years. Enough time for life to start to stumble, to adapt, to diversify, to become aware. Enough time for oceans to form, for continents to shift, for forests to grow, and ice ages to come and go. Enough time for something to evolve that can look up at the stars and wonder where they came from. We got lucky in a sense. Or maybe it's not luck. Maybe it's inevitability. In a galaxy with hundreds of billions of stars, countless G-type stars like the Sun, countless rocky planets and habitable zones, maybe life is simply what happens when you give chemistry enough time and stability. But let's not get ahead of ourselves. We're still on the main sequence, still in the long, steady burn. What's happening inside the Sun right now, deep in the core, at a temperature of 15 million Kelvin and a pressure 250 billion times Earth's atmospheric pressure, hydrogen nuclei are fusing into helium. The process is slow by particle physics standards, but staggeringly fast when you add up all the reactions happening simultaneously. Every second, about 620 million tons of hydrogen is converted into 616 million tons of helium. The missing 4 million tons, about the mass of a large asteroid, is converted into pure energy. That energy is released as gamma rays, high-energy photons that begin a long, chaotic journey outward. In the core, the density is so high that a gamma-ray photon can't travel more than a fraction of a millimeter before it collides with another particle and is absorbed. The particle re-emits the photon, often at a slightly lower energy, and the process repeats. Over and over, millions of times. It takes on average about 100,000 to 200,000 years for a photon created in the Sun's core to reach the surface. Not because the distance is so great, the Sun's radius is only 700,000 kilometers, but because the path is impossibly tangled. The photon zigzags, bounces, is absorbed and re-emitted countless times, gradually working its way outward through the radiation zone, then through the convection zone, until finally it reaches the photosphere and escapes into space. 8 minutes later, it reaches Earth. And maybe it lands on your face, warming your skin. That photon is ancient. It began its journey in the core when woolly mammoths still walked the Earth, when the Sahara was green, when humans were just beginning to paint on cave walls. And now, it's here touching you, completing a journey that started long before you were born. The Sun is not just burning, it's communicating. Every photon carries information about the temperature of the core, the composition of the plasma, the rate of fusion. By studying the sun's light, astronomers can peer into its interior, can understand processes that happen in conditions we could never recreate on Earth. One of the most remarkable techniques is called helioseismology. Just as geologists study earthquakes to understand Earth's interior, astronomers study the sun's oscillations, tiny rhythmic changes in its surface to map its internal structure. The sun rings like a bell, vibrating in thousands of different modes, and each mode tells us something about the layers beneath. Through helioseismology, we've measured the depth of the convection zone, the rotation rate of the core, even the abundance of helium in different regions. We know the sun more intimately than almost any other star because we can see it so clearly, because we live so close. And what we've learned is the sun is stable, yes, but not static. It's dynamic. It churns, it vibrates, it breathes. Its magnetic field twists and tangles, creating sunspots, flares, coronal mass ejections. Every 11 years, the magnetic field flips north, becomes south, south becomes north, and the cycle begins again. We've been observing the solar cycle since the early 1600s when Galileo first turned his telescope toward the sun and saw the dark spots moving across its surface. For centuries, we didn't understand what they were. We didn't know about magnetic fields, about plasma physics, about fusion. We just knew the sun had blemishes, and they came and went in a rhythm. Now we understand. Sunspots are regions where the magnetic field is so strong, it suppresses convection, preventing hot plasma from rising to the surface. The result is a cooler, darker patch, still blindingly bright, but less so than the surrounding photosphere. During solar maximum, when the sun's magnetic field is most tangled and active, dozens of sunspots can appear at once. During solar minimum, the sun's surface can be spotless for weeks at a time, and every so often, the magnetic field becomes so twisted that it snaps, releasing a burst of energy called a solar flare. The largest flares release as much energy as 1 billion hydrogen bombs. If directed toward Earth, they can disrupt satellites, interfere with radio communications, even damage power grids. In 1859, as we mentioned earlier, the most powerful solar storm ever recorded struck Earth. The Carrington event, named after astronomer Richard Carrington, caused auroras visible as far south as Cuba and Hawaii. Telegraph wires caught fire. Operators received electric shocks. If a similar event happened today, it could cause trillions of dollars in damage. The sun is gentle mostly, but it's not harmless. We live inside a star's sphere of influence. The solar wind, a stream of charged particles flowing outward from the sun at hundreds of kilometers per second, fills the entire solar system, creating a bubble called the heliosphere. Beyond that bubble, about 120 astronomical units from the sun, interstellar space begins. Voyager 1 crossed that boundary in 2012, becoming the first human-made object to leave the heliosphere. It's now more than 14 billion miles from Earth, still transmitting data, still traveling through the dark between the stars. And yet, it carries with it a faint trace of the sun's influence, the last whispers of the solar wind. We are in a very real sense living inside the sun's atmosphere, protected by it, warmed by it, shaped by it. And the sun, in turn, is shaped by us. Not physically, of course, but in the sense that we are the sun's witnesses. We are the part of the universe that looks back at the sun and understands what it is, where it came from, how long it will last. The sun has been burning for 4.6 billion years. It will burn for another 5 billion, perhaps a bit more. And then slowly the hydrogen in the core will run out. The fusion will stop, the balance will tip, and the long, steady burn will come to an end. But that's still far away. For now, the sun holds. The core burns, the photons rise, and life, fragile and strange and beautiful, continues here on this small planet, orbiting a star that is neither the brightest nor the dimmest, but simply perfectly enough. There comes a moment in every star's life when the fuel runs low. Not suddenly, not dramatically, just gradually, quietly. The core burns through its hydrogen atom by atom until one day there's nothing left to fuse. And then paradoxically, the star doesn't dim. It doesn't shrink. It doesn't fade away peacefully. It swells, it brightens, it becomes a monster. This is the red giant phase, and it's one of the strangest, most counterintuitive chapters in a star's story. The beginning of the end, yes, but also a period of renewed violence, of transformation, of burning brighter than ever before. Not because the star is stronger, but because it's dying. Imagine standing on Earth 7 billion years from now. The sun has exhausted the hydrogen in its core. Fusion has stopped there, but it continues in a thin shell surrounding the inert helium core. That shell burns hotter, fiercer than the core ever did. And the energy it releases pushes the outer layers of the sun outward. Slowly, over millions of years, the sun expands. Its surface cools as it stretches, shifting from yellow to orange to red. But even though it's cooler, it's vastly larger, and its total luminosity increases by hundreds, then thousands of times. Mercury is swallowed first, then Venus, and then, depending on the exact details of the expansion, possibly Earth. If Earth survives, it won't be recognizable. The oceans will have boiled away long before the sun reaches us. The atmosphere will be stripped. The surface will be molten rock glowing red in the bloated light of a star that no longer resembles the one that gave us life. This is what happens when a star runs out of hydrogen in its core, not peace, not quiet, expansion, heat. A final desperate attempt to keep burning. The term red giant was first used in the early 20th century after astronomers began categorizing stars by their color and luminosity. When they plotted stars on the Hertzsprung-Russell diagram, they noticed a cluster of cool, luminous stars in the upper right corner, stars that were red in color but far brighter than they should be for their temperature. The only explanation: these stars must be enormous, hundreds of times larger than the sun. Giants. We now know that red giants represent a transitional phase. Stars spend billions of years on the main sequence fusing hydrogen in their cores, and then in a cosmically brief period, just a few 100 million years, they swell into giants before moving on to whatever comes next. For stars like the sun, what comes next is a planetary nebula and a white dwarf. But we'll get to that. For now, let's focus on the giant phase itself, because it's here that some of the most important chemistry in the universe takes place. When the hydrogen in the core is exhausted, fusion stops. Without the outward pressure from fusion to balance gravity, the core begins to contract. As it contracts, it heats up the same principle we saw during the star's formation. Compression generates heat. Eventually, the core becomes hot enough that the shell of hydrogen surrounding it ignites. This shell burns hotter and faster than the core ever did because it's under more pressure, squeezed between the contracting helium core below and the weight of the star's outer layers above. The energy from this shell burning pushes the outer envelope outward. The star balloons in size. Its radius can increase by a factor of 100 or more. If you place the sun at the center of its future red giant self, its surface would extend past the orbit of Mars. And yet, despite this enormous size, the surface temperature drops. The outer layers are so far from the core that they cool to around 3,000 to 4,000 Kelvin. The star glows red. Here's the strange part. Even though the surface is cooler, the star is far more luminous. Luminosity depends on both temperature and surface area. And when a star's radius increases by a factor of 100, its surface area increases by a factor of 10,000. The cooling effect is more than offset by the sheer size. A red giant version of the sun will shine with the light of several thousand suns. Not because it's burning hotter, but because it's burning bigger. This phase doesn't last forever. Eventually, the helium core becomes hot and dense enough, about 100 million Kelvin, for a new type of fusion to begin: helium fusion. 3 helium nuclei fuse together to form a single carbon nucleus in a process called the triple alpha process. It's called that because helium nuclei are also known as alpha particles, and it takes 3 of them to make carbon. This process was theorized in the 1950s by the British astrophysicist Fred Hoyle. At the time, scientists were puzzled by the abundance of carbon in the universe. Carbon is essential for life, yet the conditions required to create it seemed impossibly specific. The temperature had to be just right. The density had to be just right. And even then, the reaction should have been too slow to produce much carbon. Hoyle realized there must be a resonance, a quantum mechanical quirk that makes the reaction far more likely than it should be. He predicted the existence of a specific energy level in the carbon nucleus 1 that would allow the triple alpha process to occur efficiently. In 1957, experiments confirmed Hoyle's prediction. The resonance existed. Carbon could form in the cores of red giants. And because carbon is the foundation of organic chemistry, this discovery was, in a sense, an explanation for why we exist. We are here because dying stars cook carbon in their cores. When helium fusion begins, the star stabilizes at least temporarily. The red giant shrinks slightly and settles into a new equilibrium, burning helium in the core and hydrogen in a shell around it. This phase is shorter than the main sequence, just a few 100 million years for a sun-like star, but it's stable enough. And then the helium runs out. For stars with more than about 8 times the mass of the sun, the story doesn't end with carbon. The core contracts again, heats up again, and ignites the next fuel-carbon fusion. Carbon nuclei fuse into neon and magnesium. Then neon fuses into oxygen. Oxygen fuses into silicon. Silicon fuses into iron. Each stage burns faster than the last. Carbon fusion lasts a few thousand years. Neon fusion lasts a few years. Oxygen fusion lasts a few months. Silicon fusion lasts a few days. The star becomes an onion. Layers upon layers of different elements, each one burning in a shell around the next. Hydrogen burning in the outermost shell, helium below that, carbon below that, neon, oxygen, silicon, and at the very center, an inert core of iron. Iron is the endpoint, the most stable nucleus. Fusing iron doesn't release energy, it consumes energy. So, when the core turns to iron, fusion stops, permanently. And the star has seconds to live. But we're getting ahead of ourselves. Let's stay with the red giants for now. The star is too small to reach iron, the ones like our sun that will never explode. One of the most famous red giants in the night sky is Betelgeuse, the bright red star marking the shoulder of Orion the Hunter. Even to the naked eye, Betelgeuse looks different from other stars. It's noticeably red, almost orange, and it flickers slightly, a result of its massive turbulent atmosphere. Betelgeuse is a supergiant far larger and more massive than a typical red giant. It's about 20 times the mass of the Sun, and roughly 1,000 times its diameter. If you place Betelgeuse at the center of our solar system, its surface would extend past the orbit of Jupiter. Let that sink in for a moment. A single star, large enough to swallow 4 planets. Betelgeuse is nearing the end of its life. It's already fused hydrogen, helium, carbon, and neon in its core. Right now, it's likely burning oxygen or silicon, which means it could explode as a supernova at any time tomorrow or 100,000 years from now. On cosmic timescales, those are equivalent. In late 2019 and early 2020, astronomers noticed something unusual. Betelgeuse was dimming, significantly. It dropped to about 40% of its normal brightness, sparking speculation that it was about to explode. People around the world watched the sky. News outlets ran stories. Astronomers trained their telescopes on Orion. For a few months, it felt like we were about to witness one of the most spectacular events in the universe. But Betelgeuse didn't explode. Instead, observations revealed that the dimming was caused by a massive cloud of dust, likely ejected by the star itself, that temporarily blocked our view. The dust has since dissipated, and Betelgeuse has returned to its normal brightness. It will explode eventually, just not yet. When it does, the supernova will be visible even in daylight. It will be as bright as the full moon, perhaps brighter, and it will remain visible for weeks or months. It will be one of the most extraordinary astronomical events in human history, and will be perfectly safe. Betelgeuse is about 640 light-years away, far enough that the explosion poses no threat to Earth. We'll simply have a front-row seat to the death of a giant. Not all red giants are supergiants, of course. Most are more modest. Stars like Aldebaran, the orange eye of Taurus, or Arcturus, the brightest star in the northern celestial hemisphere. These are red giants in the truest sense, cool, luminous, large, but not monstrous. Arcturus is particularly interesting. It's about 1.5 times the mass of the Sun and 25 times its radius, which makes it relatively small for a red giant. But it's incredibly bright, about 170 times more luminous than the Sun, and it has an unusual motion through the galaxy. Arcturus is moving quickly relative to the other stars in our neighborhood, which suggests it's an intruder, a star that formed elsewhere and is just passing through. In about 500,000 years, it will have moved on, becoming fainter and fainter until it's no longer visible to the naked eye. It's a reminder that the night sky is not permanent. Stars move, they age, they change. The constellations you know will not be the constellations your distant descendants know. Here's a question worth pondering. What will happen to Earth when the Sun becomes a red giant? The short answer is nothing good. Long before the Sun swells to engulf the inner planets, its increased luminosity will make Earth uninhabitable. As the Sun burns hotter in its hydrogen shell, its brightness will increase. The oceans will begin to evaporate. Water vapor is a greenhouse gas, so the more water that enters the atmosphere, the warmer Earth will become. This creates a runaway greenhouse effect. Within 1 billion years, possibly sooner, the oceans will be gone. The atmosphere will be thick with steam and carbon dioxide. Surface temperatures will exceed the boiling point of water. Earth will resemble Venus, a scorched, lifeless rock with a crushing, toxic atmosphere. And that's just the beginning. As the Sun continues to swell, even the rocks will melt. The surface will glow red hot. Any remaining atmosphere will be stripped away by the solar wind. If Earth somehow survives being swallowed, and it might because the Sun will lose a significant amount of mass as it expands, which will weaken its gravitational pull and cause the planets to drift outward, it will be nothing more than a charred cinder, orbiting a dying star in the cold and dark. Life, of course, will be long gone by then. If humanity still exists, we'll have left Earth billions of years earlier, either by choice or by necessity. Perhaps we'll have settled other star systems. Perhaps we'll have found ways to survive that we can't even imagine yet. Or perhaps we'll be gone, and some other form of intelligence will inherit the galaxy. But the Sun will continue its transformation, indifferent to the fate of the worlds it once warmed. There's something humbling about this, isn't there? The Sun, which seems so eternal, so unchanging, is on a timer. It's been counting down since the moment it was born. And while the timer is long billions of years, it's not infinite. Nothing lasts forever. Not stars, not planets, not life. But endings are also beginnings. Because when a star swells into a red giant, it's not just dying, it's creating. In the cores and shells of red giants and supergiants, nuclear fusion forges new elements. Carbon, nitrogen, oxygen, neon, magnesium, silicon. Elements that didn't exist when the star was born. Elements that will be scattered into space when the star dies. Those elements will drift through the galaxy, mixing with clouds of hydrogen, seeding the next generation of stars. And some of those elements will find their way into planets, into oceans, into living things. Every breath you take contains nitrogen forged in the core of a red giant. Every bone in your body contains calcium created in a dying star. The iron in your blood was cooked in the final moments of a supergiant's life. You are made of endings. We all are. And in that sense, the death of a star is not a tragedy. It's a gift, a transformation, an act of cosmic generosity. Red giants don't just die, they give. They release their treasures, the elements they've spent millions of years creating, back into the galaxy, so that new stars, new planets, new life can form. It's a cycle. Birth, life, death, rebirth. Over and over, across billions of years, across trillions of stars. And we are part of that cycle, not separate from it, not above it. We are the universe experiencing itself, atoms that were once locked inside dying stars, now walking, thinking, wondering. For now, the sun is still on the main sequence, still stable, still burning hydrogen in its core, but the clock is ticking, the fuel is finite, and one day, billions of years from now, the sun will begin its final transformation. It will swell, it will redden, it will become something vast and strange and beautiful. And then, when the burning is done, it will shed its outer layers gently like a flower releasing its petals. When a star like the sun dies, it doesn't explode. It whispers. It releases its outer layers slowly, gently, like breath leaving lungs for the last time. And what remains is something so beautiful, so delicate, that early astronomers thought they were looking at planets forming in the distant solar systems. They were wrong. But the name stuck. These are planetary nebulae, and they are not birthplaces. They are graves, glowing luminous graves where stars shed their skin and leave behind only their hearts, small, hot, dense cores called white dwarfs. This is how most stars end, not with violence, not with fury, but with grace. For stars between about 0.8 and 8 times the mass of the sun, which represents the vast majority of stars in the galaxy, the red giant phase is followed by something quieter. The outer envelope, bloated and tenuous, is no longer gravitationally bound to the core. Stellar winds, streams of particles flowing outward from the star, begin to push it away. Slowly at first, then faster. The outer layers drift into space, expanding, thinning, forming a shell of glowing gas around the dying core. This shell is what we call a planetary nebula. And when the hot core is finally exposed, blazing at temperatures of 100,000 Kelvin or more, its ultraviolet radiation ionizes the surrounding gas, causing it to glow in brilliant colors. Red from hydrogen, green from oxygen, blue from helium. The result is one of the most visually stunning objects in the universe, a cosmic flower blooming in the dark. The term planetary nebula was coined in the late 18th century by the German-British astronomer William Herschel. He was conducting a survey of the sky, cataloging everything he could see through his telescope, when he came across several small, round, greenish objects. They looked to him like planets, hence the name. Of course they weren't planets, they weren't even close. But by the time astronomers realized what they actually were, the name had already become standard. So, we're stuck with it, a historical misnomer that persists to this day. Herschel had no idea what he was looking at. It would be more than a century before astronomers understood the true nature of planetary nebulas, and even longer before they understood the physics behind them. In the 1920s, the American astronomer Henry Norris Russell proposed that planetary nebulae were the ejected outer layers of dying stars. In the 1950s, advances in spectroscopy confirmed this. And by the 1980s, space telescopes like the Hubble had revealed planetary nebulae in exquisite detail, showing structures far more complex than anyone had imagined. Some are round and symmetrical. Others are elongated, bipolar shaped like hourglasses or butterflies. Some have multiple shells layered like an onion. Others have jet streamers, knots of denser material embedded in the outflow. No two are exactly alike. Each one is a unique signature, a final portrait of a star's last breath. One of the most famous planetary nebulae is the Ring Nebula, also known as Messier 57 or M57. It's located in the constellation Lyra, about 2,300 light-years from Earth, and it's one of the brightest and most easily observed planetary nebulae in the night sky. Through a small telescope, it looks like a ghostly smoke ring suspended in space. Through larger telescopes, you can see more detail, the faint outer shell, the brighter inner ring. And at the very center, a tiny blue-white dot, the white dwarf, the remnant core of the star that created this nebula. The Ring Nebula formed about 1,600 years ago when the central star shed its outer layers. The gas is still expanding, moving outward at about 20 to 30 kilometers per second. In another 10,000 years or so, the nebula will have dispersed, completely fading into the interstellar medium, indistinguishable from the background. But, for now, it glows. A monument to a star that no longer exists, at least not in the form it once held. Another famous example is the Helix Nebula, sometimes called the Eye of God because of its striking appearance. It's one of the closest planetary nebulae to Earth, just 650 light-years away, and it's enormous, about 2.5 light-years in diameter, roughly half the distance from the Sun to the nearest star. The Helix Nebula has a complex structure. There's the main shell expanding outward, but there are also smaller structures. Within the shell cometary knots, they're called dense clumps of gas with long tails shaped by the radiation from the central star. These knots are thought to be remnants of denser regions in the original star's outer layers material that survived the ejection and is now slowly evaporating under the intense ultraviolet light. Observing the Helix Nebula is like looking at a dissection of stellar death layer by layer, structure by structure. Every detail tells a story about the star that was about the forces at play during its final transformation. And then there's the Cat's Eye Nebula, one of the most complex planetary nebulae known. It has at least 11 concentric shells, each one ejected at a different time, each one shaped by different processes. There are jets. There are spiral patterns. There are regions of shocked gas where fast-moving material slams into slower-moving material. The Cat's Eye Nebula is a puzzle. Astronomers still don't fully understand how it formed. The prevailing theory is that the central star had a companion, a binary system, and the interaction between the two stars during the red giant phase created the complex outflows we see today. Binary stars, it turns out, are very common. More than half of all stars exist in binary or multiple systems. And when one member of a binary becomes a red giant, the dynamics can get complicated. The giant can transfer mass to its companion, or the companion's gravity can distort the giant's shape, causing it to eject material in specific directions, rather than uniformly. This might explain why so many planetary nebulae are not spherical. They're bipolar or elliptical or wildly asymmetric. The presence of a companion star sculpts the outflow, turning what might have been a simple expanding shell into something far more intricate. But not all planetary nebulae require a binary companion. Even single stars can create complex shapes depending on how the star rotates, how its magnetic field is structured, and how the mass loss occurs over time. The variety is astonishing and humbling because each planetary nebula is the end of a story that lasted billions of years. A star was born, lived, aged, and finally gently let go. At the center of every planetary nebula is a white dwarf. This is what remains of the star after it has shed its outer layers. It's no longer fusing anything. It no longer generates energy through nuclear reactions. It's just a hot, dense ball of carbon and oxygen sometimes, with a thin layer of helium or hydrogen on the surface, slowly cooling over trillions of years. White dwarfs are small, very small, about the size of Earth despite containing roughly the mass of the Sun. Imagine compressing the Sun, a ball of plasma, 1.4 million kilometers in diameter, down to the size of our planet. The density is almost incomprehensible. A teaspoon of white dwarf material would weigh about 15 tons. That's roughly the weight of 2 elephants compressed into the volume of a sugar cube. This density is supported not by thermal pressure or fusion, but by something called electron degeneracy pressure. It's a quantum mechanical effect. Electrons, being fermions, obey the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. When you compress matter to extreme densities, the electrons resist further compression, not because they're hot, but because there's simply no room left for them to occupy. This pressure is immense. It can support the mass of a star, even without fusion, for as long as the universe has existed. But there's a limit. If a white dwarf exceeds about 1.4 times the mass of the Sun, a threshold known as the Chandrasekhar limit electron degeneracy pressure is no longer enough. The white dwarf collapses, and depending on the circumstances, it either becomes a neutron star or it triggers a supernova. We'll come back to that. For now, let's focus on the white dwarfs that stay within the limit, the ones that simply cool and fade. The first white dwarf ever discovered was Sirius B, the companion to Sirius, the brightest star in the night sky. Sirius is actually a binary system. Sirius A is a main sequence star about twice the mass of the Sun, blazing hot and blue-white. Sirius B is its companion, a white dwarf about the size of Earth, glowing faintly in the overwhelming glare of its partner. Sirius B was first observed in 1862 by the American astronomer Alvin Graham Clark, who was testing a new telescope lens. He noticed a faint point of light near Sirius and realized it matched predictions made years earlier by Friedrich Bessel, who had noticed that Sirius wobbled slightly in its motion across the sky, a sign that it was being tugged by an unseen companion. When astronomers measured the mass and size of Sirius B, they were astonished. It was as massive as the Sun, but no larger than Earth. The implications were profound. Matter could exist in states far denser than anyone had imagined. Sirius B is now one of the most studied white dwarfs, a nearby laboratory for testing theories of stellar evolution and quantum mechanics. It's also a preview of the Sun's future. In about 7 to 8 billion years after the Sun has exhausted its helium, after it has swelled into a red giant and shed its outer layers, it will become a white dwarf. Small, dense, cooling slowly in the dark. What will happen to Earth when that day comes? If Earth survives the red giant phase, and that's a big, if it will orbit a white dwarf, the Sun will no longer emit the warm yellow light that made life possible. Instead, it will glow faintly in ultraviolet, invisible to human eyes, providing almost no heat. Earth will be frozen, lifeless, a barren rock orbiting a dying ember. But even in death, white dwarfs are not entirely inert. They cool, yes, but they cool very slowly. It takes trillions of years for a white dwarf to radiate away all its residual heat and become a black dwarf, a cold, dark lump of carbon and oxygen invisible except for the gravitational influence it exerts on nearby objects. No black dwarfs exist yet. The universe is only 8 billion years old, far too young for any white dwarf to have cooled completely. The oldest white dwarfs we've observed are still glowing, still emitting faint heat, still waiting for the long, slow fade into darkness. In a sense, white dwarfs are the longest-lived objects in the universe. They don't burn out quickly like massive stars. They don't collapse or explode. They just persist, cooling by a few degrees every billion years, outlasting galaxies, outlasting everything, except perhaps protons themselves. There's something poignant about that, isn't there? That the quietest deaths are also the most enduring. Here's a question worth considering. What does it mean for something to die? In human terms, death is an end, a stopping. But in cosmic terms, death is a transformation. The atoms that made up the star don't vanish. They drift into space carried by stellar winds, mixing with the interstellar medium, becoming part of the raw material for the next generation of stars. The oxygen you're breathing right now was once inside a star. It was created through fusion in the core of a red giant, released during the planetary nebula phase, and eventually incorporated into the molecular cloud that gave birth to the Sun and the solar system. You are breathing stardust, literally. And when the Sun dies, when it sheds its outer layers and forms its own planetary nebula, The elements it releases will drift through the galaxy. They might, billions of years from now, become part of a new star, a new planet, a new form of life. Nothing is truly lost. It only changes form. Planetary nebulae are beautiful, not just because of their colors and shapes, but because of what they represent. They are proof that endings can be gentle, that death can be a gift, that what seems like loss is actually a transfer, a passing on of something precious. Every planetary nebula you see in a photograph, the ring, the helix, the cat's eye, the dumbbell, the butterfly, is a star in the act of giving, releasing its treasures, returning to the universe the elements it spent billions of years creating: carbon, nitrogen, oxygen, the building blocks of life. These nebulae glow for a few thousand years, maybe 10 or 20,000 at most, and then they fade. The gas disperses, the light dims, and all that remains is the white dwarf cooling, slowly waiting. But the elements don't disappear. They linger, they drift, they become part of the next story. And maybe they become part of someone who looks up at the stars and wonders where they came from. The sun will one day create its own planetary nebula. It will be small, probably not as spectacular as some of the ones we've observed, but it will be there glowing softly in the place where a yellow star once burned. And if any intelligent beings are still around to see it, whether they're descendants of humanity or something entirely new, they'll look up and see not an ending, but a kind of beauty that only comes from letting go. For now, though, the sun still burns, the core still fuses, the light still reaches Earth, and life in all its fragile complexity continues. But the white dwarf is waiting, patient, inevitable, a future written in the physics of stellar evolution, in the slow burn of hydrogen and helium, in the gentle release of outer layers into the cosmic wind. And when that future arrives, it will not be a tragedy. It will be a transformation, an act of quiet grace, a star becoming something new in the only way it knows how. But some stars don't have the luxury of dying gently. Some stars are too massive, too hot, too full of fuel to simply shed their layers and fade. For them, the end is not a whisper. It's a scream. For a few weeks, a single dying star can outshine an entire galaxy. Billions upon billions of stars, all their light, combined all their photons streaming into space, and one exploding star is brighter than all of them. This is a supernova, not a gentle release, not a quiet fade, but a detonation so violent, so energetic, that it tears the star apart from the inside out, scattering its remains across light years, seeding the galaxy with elements that didn't exist a moment before. This is how massive stars die. And this is how the universe becomes rich enough to build planets, oceans, and you. A supernova begins not with fire, but with poison, iron, the most stable element, the end point of fusion. When a massive star, one, with more than about 8 times the mass of the sun, fuses silicon into iron in its core, it has reached the end of the line. Every fusion reaction up to this point has released energy. Hydrogen to helium releases energy. Helium to carbon releases energy. Carbon to oxygen, oxygen to silicon. All of it releases energy, generating the outward pressure needed to balance gravity. But iron is different. Fusing iron doesn't release energy, it consumes energy. The reaction is endothermic, and that means the moment the core turns to iron, the star is doomed. There's no more fuel, no more reactions to generate pressure. Just an inert ball of iron about the size of Earth, sitting at the center of a massive star, held up only by electron degeneracy pressure. And then gravity wins. The core collapses. Not slowly, not over millions of years, but in less than a second. One moment the core is stable. The next it's falling inward at nearly a quarter of the speed of light. In a fraction of a second, the core shrinks from the size of Earth to the size of a city, maybe 10 kilometers across. The density becomes so extreme that protons and electrons are crushed together, forming neutrons. The core becomes a neutron star, or if it's massive enough, it doesn't stop there. It collapses all the way into a black hole. But before that happens, something extraordinary occurs. The infalling material hits the incompressibly dense neutron core and bounces. Like a ball hitting a wall, like a wave crashing against a cliff. The rebound sends a shock wave racing outward through the star, ripping through the layers of silicon, oxygen, carbon, helium, hydrogen. And the star explodes. The outer layers are blasted into space at speeds of 10,000 to 30,000 kilometers per second, up to 10% the speed of light. The explosion releases about 10 or 44 joules of energy, more energy than the sun will produce in its entire 10 billion year lifetime. For a few weeks, the supernova is the brightest object in its galaxy. From Earth, a supernova in the Milky Way would be visible in daylight. It would cast shadows at night. It would be brighter than the full moon, perhaps brighter than anything in the sky except the sun itself. And then slowly it would fade. The light would dim, the debris would cool, and all that would remain is a glowing cloud of gas, a supernova remnant expanding into the interstellar medium, carrying with it the ashes of a star. Humans have been witnessing supernova for as long as we've been looking at the sky. We just didn't always know what they were. In 1054, CE, Chinese and Arab astronomers recorded the sudden appearance of a guest star in the constellation Taurus. It was so bright it was visible during the day for 23 days, and it remained visible at night for nearly 2 years before fading from view. What they were seeing was a supernova, and what remains today nearly 1,000 years later is the Crab Nebula, a vast cloud of glowing gas still expanding, still carrying the energy of the long-ago explosion. At the center of the Crab Nebula is the Crab Pulsar, a neutron star spinning 30 times per second, emitting beams of radiation like a cosmic lighthouse. Every rotation the beam sweeps past Earth and we see a pulse of light. 30 pulses per second, perfectly regular, like a clock ticking in the void. The Crab Pulsar is one of the most studied objects in astronomy. It's a laboratory for extreme physics, a place where matter is compressed to densities we can barely comprehend, where magnetic fields are trillions of times stronger than Earth's, where the laws of quantum mechanics and general relativity collide. And it's all because of a star that exploded nearly a millennium ago. Another famous historical supernova occurred in 1604, observed by the German astronomer Johannes Kepler. Kepler's supernova, as it's now called, appeared in the constellation Ophiuchus and was visible to the naked eye for over a year. Kepler himself studied it, carefully recording its brightness and position, trying to understand what it was. He concluded correctly that it was a star that had suddenly appeared where none had been before. But he didn't understand the mechanism. He couldn't. The physics of stellar evolution, the concept of nuclear fusion, the nature of neutron stars, all of that was centuries away. Kepler's supernova was the last supernova observed in the Milky Way with the naked eye. It's been over 400 years. We're overdue. Astronomers estimate that a supernova should occur in the Milky Way on average once or twice per century. But the galaxy is large and most of it is hidden behind dust. Many supernovae likely go unnoticed, occurring on the far side of the galaxy where we can't see them. Still, we watch. We wait. Because when the next supernova occurs in the Milky Way, it will be one of the most significant astronomical events in modern history. Betelgeuse, as we mentioned earlier, is a prime candidate. So is Eta Carinae, an unstable hypergiant that has already undergone several massive eruptions. Either one could explode within the next 100,000 years, or tomorrow. We don't know. But the most important supernova in modern astronomy didn't occur in the Milky Way. It occurred in a neighboring galaxy, the Large Magellanic Cloud, on February 23, 1987. It was called SN 1987A, and it changed everything. SN 1987A was the closest supernova to Earth since Kepler's supernova in 1604, and it was the first to be studied with modern instruments. Telescopes around the world turned to observe it. Spectrographs analyzed its light. And for the first time, astronomers were able to watch a supernova in real time from the initial explosion to the formation of the remnant. But the most remarkable observation didn't come from telescopes. It came from underground. About 3 hours before the supernova became visible, a burst of neutrinos passed through Earth. Neutrinos are ghostly particles barely interacting with matter. Trillions pass through your body every second from the sun, and you never notice. But during a supernova, the number of neutrinos produced is so enormous that even a tiny fraction of them can be detected. 2 detectors, Kamiokande in Japan and IMB in the United States, recorded a sudden spike in neutrino events. 11 neutrinos in Kamiokande, 8 in IMB. Out of the trillions upon trillions that passed through the detectors, only 19 were captured. But those 19 neutrinos confirmed something profound. They confirmed that supernovae are powered by core collapse, that most of the energy is carried away by neutrinos, and that our models of stellar death were at least in broad strokes correct. It was one of the most important detections in the history of physics. A handful of particles traveling 168,000 light years from a dying star arriving at Earth just in time to tell us what happened in the core of a collapsing giant. Think about that for a moment. Neutrinos created in the final seconds of a star's life, passing through the entire star, through 168,000 light years of space, through the Earth itself, and into a detector deep underground. A message from a dying star written in particles so elusive they barely exist. And we heard it. Supernovae don't just destroy, they create. During the explosion, the temperatures and pressures are so extreme that new elements are forged elements that cannot form in the core of a star under normal conditions. Elements heavier than iron, gold, silver, platinum, uranium. All the elements on the periodic table heavier than iron were created in supernovae, or in the collisions of neutron stars. Every gold ring, every silver coin, every platinum catalyst in a car's exhaust system, they all came from exploding stars. The process is called R-process nucleosynthesis, where R stands for rapid. Neutrons are captured by atomic nuclei so quickly that there's no time for decay. The nuclei grow heavier and heavier, building up elements that couldn't exist otherwise. It's violent, it's chaotic, it's extraordinarily rare, but it's the only way to make the heaviest elements. Without supernovae, the universe would be a simpler place. Just hydrogen, helium, and a little lithium. No carbon, no oxygen, no iron, no gold, no uranium, no planets, no oceans, no life. You exist because stars exploded. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in the cores of dying stars and scattered into space by supernovae. We are not just made of stardust, we are made of star death. Here's a question that haunts astronomers. What would happen if a supernova occurred close to Earth? The answer depends on the distance. A supernova closer than about 25 light years would be catastrophic. The gamma rays and X-rays from the explosion would strip away Earth's ozone layer, exposing the surface to lethal ultraviolet radiation from the sun. The explosion would also produce a shower of cosmic rays high-energy particles that could damage DNA, increase cancer rates, and disrupt the atmosphere. Mass extinctions in Earth's past might have been caused by nearby supernovae. There's evidence isotopes of iron-60 in ocean sediments that suggest a supernova occurred within 300 light years of Earth about 2 to 3 million years ago. It wasn't close enough to cause a mass extinction, but it might have affected the climate, the radiation environment, even the evolution of life. Fortunately, there are no stars close enough to pose an immediate threat. The nearest candidate, Betelgeuse, is about 640 light years away, far enough that when it explodes, the show will be spectacular but harmless. We'll see it brighten over the course of a few days, reaching a peak brightness roughly equal to the full moon. It will be visible during the day. At night, it will cast shadows. And for weeks, maybe months, we'll have a second source of bright light in the sky, a glowing ember in the shoulder of Orion. And then it will fade. Over the course of a year or two, it will dim until it's no longer visible to the naked eye. And all that will remain is a faint nebula expanding slowly, glowing faintly, a memorial to a star that once shone brighter than almost anything else in the night sky. But the explosion itself, the shock wave, the light, the gamma rays, all of that takes time to reach us. We won't see it happen in real time. We'll see it 640 years after it happens. The star might have already exploded. The light might already be on its way. And we wouldn't know until it arrives. That's the strange thing about looking at stars. You're always looking into the past. The light you see left the star years, decades, centuries, millennia ago. The star might still be there, or it might be gone. There's no way to know until the light reaches you. In a sense, supernovae are messages from the past, letters written in light, carried across the void, arriving long after the event itself. And when we study them, when we analyze their spectra, when we measure their distances and brightnesses, we're reading those letters. We're learning about stars that lived and died before humans existed, before Earth formed, before the sun ignited. Supernovae leave behind remnants, vast clouds of gas, glowing with the energy of the explosion, still expanding centuries or millennia later. The Crab Nebula, as we mentioned, is one such remnant. Another is the Vela supernova remnant, created by a supernova that occurred about 11,000 years ago, just 800 light-years from Earth. It's one of the closest and brightest supernova remnants in the sky, though it's only visible from the southern hemisphere. At the center of the Vela remnant is a pulsar spinning 11 times per second. And surrounding it is a vast shell of glowing gas still expanding at thousands of kilometers per second, still carrying the heat and energy of an explosion that occurred before the first cities were built. These remnants are not just beautiful, they're scientifically invaluable. By studying the composition of the gas, astronomers can learn what elements were created in the supernova. By measuring the expansion rate, they can estimate the energy of the explosion. And by observing the central neutron star, or black hole, they can test theories of extreme physics. But more than that, supernova remnants are recycling centers. They mix the heavy elements created in the explosion with the surrounding interstellar medium, enriching it, making it more complex, more capable of forming rocky planets and organic molecules. Every supernova is a gift to the galaxy. A violent, destructive, utterly catastrophic gift, but a gift nonetheless. Without supernovae, the universe would be stuck in a loop. Stars would form from hydrogen and helium. They would burn for a while, and then they would die, leaving behind white dwarfs or black holes, but no heavy elements, no enrichment, no progress. But with supernovae, the cycle changes. Stars are born, live die, and in dying, they release the elements they have created. Those elements mix with the primordial hydrogen and helium, forming new clouds, new stars, new planets. And with each generation, the universe becomes richer, more complex, more interesting. The sun is a third-generation star, maybe a fourth. It formed from a cloud that had already been enriched by earlier generations of stars, earlier supernovae. That's why the solar system has rocky planets. That's why Earth has iron at its core, silicates in its mantle, carbon and oxygen in its atmosphere. None of that would exist without supernovae. You wouldn't exist without supernovae. There's a humbling irony in that, isn't there? That the most violent events in the universe are also the most necessary. That destruction is creation. That death is life. The star that exploded to create the elements in your body didn't know you would exist. It didn't have a purpose. It just ran out of fuel, collapsed, and exploded because that's what physics demanded. And yet, here you are, a consequence of that explosion. A fragment of a star rearranged into something that can think and wonder and look back at the stars and ask, where did I come from? The answer is everywhere. You came from a cloud of hydrogen, from the core of a red giant, from the shock wave of a supernova, from a molecular cloud collapsing under its own gravity. You are the universe remembering itself. For a few weeks, that exploding star outshone everything, and then it faded. But what it left behind, the elements, the energy, the seeds of new stars that persists, that becomes part of the next chapter. And sometimes in the wreckage of that explosion, something even stranger is born. Something so dense, so extreme that it defies everything we thought we knew about matter, about space, about time itself. Imagine compressing a mountain into a teaspoon. All the rock, all the mass squeezed down until it weighs as much as 100 million tons. Now, imagine doing that to an entire star. That's a neutron star. And it's one of the strangest objects in the universe, so dense, so extreme, that it bends the very fabric of space-time around it. And if you go further, if you compress it just a little more, something even stranger happens. The star doesn't stop collapsing. It falls inward forever, creating a hole in space itself. A place where gravity is so strong that not even light can escape. A black hole. This is where stellar death becomes something beyond comprehension. Beyond anything we experience in everyday life. A place where the rules change, where matter behaves in ways that seem impossible, where the universe shows us just how strange it can be. When the core of a massive star collapses during a supernova, what's left behind depends on one thing: mass. If the remaining core is between about 1.4 and 3 times the mass of the Sun, it becomes a neutron star. If it's more than 3 solar masses, it becomes a black hole. Let's start with neutron stars, because they're extraordinary enough on their own. A neutron star is what happens when you compress the core so much that protons and electrons can no longer exist separately. The pressure is so intense that they're forced together, merging into neutrons through a process called electron capture. What you're left with is a ball of neutrons packed so tightly that there's almost no space between them. The density is almost unimaginable. A neutron star with 1.4 times the mass of the Sun is only about 20 kilometers across, about the size of a city. Manhattan, if you squeezed it into a sphere, would be roughly the same size as a neutron star containing more mass than the Sun. That means a sugar cube of neutron star material would weigh about 100 million tons, more than all the cars on Earth combined. And if you could somehow bring that sugar cube to Earth, it would fall straight through the ground, through the mantle, through the core, and out the other side, because nothing on Earth is strong enough to hold it. Neutron stars are supported not by thermal pressure or fusion, but by neutron degeneracy pressure, the same quantum mechanical effect that supports white dwarfs, but taken to an extreme. Neutrons, like electrons, are fermions, and they obey the Pauli exclusion principle. They resist being compressed into the same quantum state, and that resistance is what keeps the neutron star from collapsing further. But it's a fragile balance. Add a little more mass, and the neutron degeneracy pressure won't be enough. The star will collapse into something else. The first neutron star was discovered in 1967, though no one knew what it was at first. Jocelyn Bell Burnell, a graduate student at the University of Cambridge, was using a radio telescope to study quasars when she noticed something odd in the data, a signal, regular, repeating every 1.337 seconds like clockwork. It was so precise, so regular, that she and her supervisor, Anthony Hewish, briefly considered the possibility that it might be a signal from an alien civilization. They even jokingly called it LGM-1 for Little Green Men, but it wasn't aliens. It was a pulsar, a rapidly spinning neutron star emitting beams of radio waves from its magnetic poles. As the star rotates, the beams sweep across space like a lighthouse, and every time one passes Earth, we see a pulse. The discovery was groundbreaking. It confirmed the existence of neutron stars, which had been predicted theoretically in the 1930s by astronomers like Subramanian Chandrasekhar and J. Robert Oppenheimer, but had never been observed. In 1974, Anthony Hewish was awarded the Nobel Prize in Physics for the discovery. Jocelyn Bell Burnell was not included, a decision that remains controversial to this day. She was the one who found the signal. She was the one who recognized it as something new. But the Nobel went to her supervisor. Belle Burnell has spoken graciously about it over the years, noting that such oversights were common at the time, especially for women in science. But the scientific community has since recognized her contribution, awarding her numerous honors, including the Special Breakthrough Prize in Fundamental Physics in 2018 worth $3 million. The pulsar she discovered, now known as PSR B1919+21, is still spinning, still pulsing more than 50 years later. Pulsars are extraordinarily precise clocks. Some of them are so regular that they rival atomic clocks in accuracy. The fastest known pulsar, PSR J1782446AD, spins 716 times per second. That's more than 10 times faster than a blender. A point on its equator is moving at about 24% the speed of light. How can something spin that fast without flying apart? The answer is gravity. A neutron star's gravity is so strong, about 200 billion times stronger than Earth's, that it holds the star together, even at these ridiculous rotation speeds. The surface gravity is so intense that if you stood on a neutron star, which you couldn't, because you'd be instantly flattened, you would weigh about 10 billion times more than you do on Earth. And the magnetic fields are even more extreme. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. But some neutron stars, called magnetars, have magnetic fields 1,000 times stronger than that. These are the most magnetic objects in the universe. Their magnetic fields are so strong that they can tear atoms apart, ripping electrons from their orbits. If a magnetar were located halfway between Earth and the Moon, it would erase every credit card, hard drive, and electronic device on the planet. And if you got within 1,000 kilometers of a magnetar, the magnetic field would be strong enough to disrupt the biochemistry of your cells. You wouldn't just die. You'd cease to be matter as we know it. Magnetars occasionally release bursts of energy called starquakes. The crust of the neutron star, made of iron nuclei, locked into a crystalline lattice, shifts slightly, maybe by a millimeter, and the release of energy is staggering. In 2004, a magnetar called SGR 1806-20, located 50,000 light-years away, released a burst of gamma rays so powerful that it briefly overwhelmed every satellite in the solar system and measurably affected Earth's ionosphere. A millimeter shift, 50,000 light-years away. And we felt it here. These objects are beyond extreme. They're laboratories for physics we can't replicate on Earth. Places where the laws of quantum mechanics and general relativity collide, where matter exists in states we barely understand. But as strange as neutron stars are, they're not the strangest thing a dying star can become. If the core is too massive, more than about 3 solar masses, neutron degeneracy pressure isn't enough. The star keeps collapsing, past the neutron star stage, past any known form of matter, and it becomes a black hole. A black hole is not an object, not in the usual sense. It's a region of space-time where gravity is so strong that the curvature becomes infinite, where the escape velocity exceeds the speed of light, where once you cross the boundary, the event horizon, there's no way out, not because you're being pulled inward exactly, but because all paths, all possible trajectories through space-time point inward. Outward ceases to exist as a direction. The event horizon is the point of no return. Once you cross it, your fate is sealed. You will reach the center, the singularity, in a finite amount of time, no matter what you do. You could fire your rockets at full thrust. You could travel at 99.9% the speed of light. It doesn't matter. All roads lead to the singularity. And at the singularity, all the mass of the collapsed star is compressed into a point of infinite density. Or at least that's what general relativity predicts. Whether singularities actually exist, or whether quantum mechanics steps in to prevent them, is one of the great unsolved questions in physics. The concept of a black hole is not new. In 1783, the English clergyman and natural philosopher John Michell speculated about dark stars objects so massive and dense that light could not escape them. He was working with Newtonian gravity, which doesn't quite get the physics right, but the intuition was correct. In 1915, Albert Einstein published his theory of general relativity, which described gravity not as a force, but as the curvature of space-time. Within months, the German physicist Karl Schwarzschild found an exact solution to Einstein's equations, the Schwarzschild metric, which describes the space-time around a non-rotating black hole. Einstein himself was skeptical. He didn't believe black holes could actually form in nature. He thought they were mathematical curiosities, artifacts of the equations not real objects. But in the 1930s, Subrahmanyan Chandrasekhar and J. Robert Oppenheimer showed that if a star were massive enough, nothing could stop it from collapsing into a black hole. Chandrasekhar calculated the mass limit for white dwarfs. Oppenheimer calculated the mass limit for neutron stars, and beyond that limit, there was only one outcome: gravitational collapse. Even then, many physicists resisted the idea. Black holes seemed too strange, too extreme. Surely nature wouldn't allow such things. But nature did. And in the 1960s and 70s, astronomers began finding evidence that black holes were real. The first strong candidate was Cygnus X1, an X-ray source in the constellation Cygnus. Observations showed that it was part of a binary system orbiting a blue supergiant star. But the companion was invisible, and the X-rays suggested that matter was falling into something incredibly dense and hot. The only explanation was a black hole. Matter from the supergiant was being pulled toward the compact object, forming an accretion disk. As the matter spiraled inward, it heated up to millions of degrees, emitting intense X-rays just before crossing the event horizon. Cygnus X1 is about 15 times the mass of the Sun, and it's about 6,000 light-years away. It was the first black hole most astronomers accepted as real, and since then, we've found thousands more. In 2019, astronomers achieved something extraordinary. They took a picture of a black hole. It was the black hole at the center of the galaxy, M87, about 55 million light-years away. The black hole itself is invisible, of course, because no light escapes it. But the Event Horizon Telescope, a global network of radio telescopes working together, captured an image of the shadow of the black hole silhouetted against the glowing accretion disk. The image showed a dark circle surrounded by a bright ring of light, the photon sphere, the last orbits where light can circle the black hole before either escaping or falling in. It was one of the most important images in the history of astronomy, proof that black holes exist, proof that general relativity works even in the most extreme conditions. The black hole in M87 is enormous, about 6.5 billion times the mass of the Sun. Its event horizon is larger than our entire solar system, and it's consuming matter at a rate of about 90 Earth masses per day. But stellar mass black holes, the ones formed from the collapse of massive stars, are much smaller. A black hole with 10 times the mass of the Sun has an event horizon only about 30 kilometers in radius, smaller than a city. You could fit it inside Manhattan, and yet it contains the mass of 10 suns compressed into a region of space so small, so dense, that the curvature of space-time becomes extreme. Here's where things get strange, really strange. If you were to fall into a black hole from your perspective, it would take a finite amount of time to reach the singularity. Maybe a few seconds, maybe a few minutes, depending on the size of the black hole. You'd cross the event horizon, and then inevitably you'd reach the center. But from the perspective of someone watching you from outside, you'd never quite reach the event horizon. As you got closer, you'd appear to move slower and slower. Your clock would tick slower relative to theirs. And at the event horizon itself, time dilation becomes infinite. To the outside observer, you'd appear to freeze asymptotically approaching the horizon, but never quite crossing it. Both perspectives are correct. There's no contradiction, just a consequence of the way space-time works near a black hole. And then there's spaghettification. If you fell into a stellar mass black hole feet first, the tidal forces, the difference in gravitational pull between your head and your feet, would be enormous. Your feet would be pulled much harder than your head, stretching you vertically while compressing you horizontally. You'd be stretched into a long, thin strand like spaghetti. For supermassive black holes, the tidal forces at the event horizon are much weaker because the horizon is farther from the singularity. You could in principle cross the event horizon without being torn apart, but once inside, there's no escape. And as you got closer to the singularity, the tidal forces would eventually destroy you. Black holes don't last forever, though. Stephen Hawking showed in 1974 that black holes emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation carries energy away from the black hole, causing it to slowly evaporate. For stellar mass black holes, the evaporation time is absurdly long. A black hole with the mass of the Sun would take about 10 for 67 years to evaporate. That's a 1 followed by 67 zeros, far, far longer than the current age of the universe. But eventually, in the unimaginably distant future, all black holes will evaporate. The universe will be left with nothing but cold, diffuse radiation, the heat death, the final equilibrium. But that's trillions of years away. For now, black holes are growing, shaping the galaxies around them. And sometimes when two neutron stars collide, or when a neutron star and a black hole merge, something extraordinary happens. The collision releases a burst of gravitational waves, ripples in space-time itself, and a kilonova, a massive explosion that creates even more heavy elements than a supernova. In 2017, astronomers detected gravitational waves from a neutron star collision. It was the first time we'd observed such an event with both gravitational waves and light. And the data confirmed something remarkable. Neutron star collisions are one of the primary sources of gold, platinum, and other heavy elements in the universe. Every gold atom on Earth, every wedding ring, every gold bar in a vault was created in the collision of two neutron stars billions of years ago in a galaxy far from here. It's humbling, isn't it? That the most violent events in the universe are also the most creative. That destruction and creation are two sides of the same coin. Neutron stars and black holes are the end of the line for massive stars. But they are not the end of the story. Because the material those stars release, the gas, the dust, the heavy elements, that material drifts through the galaxy, mixing, cooling, gathering, and eventually it begins to collapse again. Gravity pulls it inward. New stars form, new planets, new chances for something unexpected to happen. The story doesn't end with death. It never does. Because in the universe, nothing is ever truly lost. It only changes form. The gas expelled by dying stars doesn't vanish into the void. It drifts. It cools. It mixes with the hydrogen and helium that's been there since the beginning. And slowly, over millions of years, gravity begins to pull it back together. The ashes of one generation become the seeds of the next. This is the cosmic circle. Birth, life, death, rebirth. Over and over, across billions of years, across countless stars. And each time the cycle repeats, the universe becomes a little richer, a little more complex, a little more capable of producing something extraordinary, like you. When the sun formed 4.6 billion years ago, it wasn't made of pure hydrogen and helium. If it had been, there would be no Earth, no rocky planets, no iron core, no silicate mantle, no oceans, no atmosphere. Just gas giants maybe orbiting a solitary star. But the molecular cloud that collapsed to form the sun had already been enriched. It contained carbon, oxygen, nitrogen, silicon, iron elements that could only have been created inside earlier stars. Stars that lived, aged, and died before the sun ever ignited. In fact, there's evidence that the formation of the solar system was triggered by a nearby supernova. When astronomers analyze meteorites, fragments of the early solar system that have survived largely unchanged, they find isotopes that shouldn't be there. Isotopes like iron-60 and aluminum-26, which have short half-lives. They decay quickly on the order of millions of years. The only way these isotopes could be present in the early solar system is if they were created shortly before the sun formed, and the only event energetic enough to create them is a supernova. So here's the story scientists suggest. About 4.6 billion years ago, a massive star exploded near a quiet molecular cloud. The shock wave from the supernova slammed into the cloud, compressing it, triggering its collapse. And as the cloud collapsed, it carried with it the debris from the supernova, iron-60, aluminum-26, and all the other heavy elements. That cloud became the sun, and from the leftover material spinning in a disk around the young star, the planets formed. Earth is built from the ashes of a star that exploded before the sun was born. Every atom heavier than helium in your body came from that star or from others like it. You are not separate from the stars, you are made of them. Astronomers classify stars by their metallicity, the abundance of elements heavier than helium. The very first stars born in the early universe, just a few 100 million years after the Big Bang, had no metals at all. They were made of pure hydrogen and helium because nothing else existed yet. These are called population 3 stars, and none of them are still alive today. They were massive, hot, and short-lived. They burned through their fuel in just a few million years, then exploded as supernovae, scattering the first heavy elements into space. The next generation population 2 stars formed from clouds enriched by those first supernovae. They have low metallicity, but not zero, and some of them are still alive today, orbiting in the halo of the Milky Way, ancient relics of the galaxy's early days. The Sun is a population 1 star. It formed from a cloud that had already been enriched by multiple generations of stars. It has relatively high metallicity. About 2% of its mass is elements heavier than helium. That might not sound like much, but it's enough to build rocky planets, enough to build life. We are 3rd generation, maybe 4th generation cosmic citizens. Our atoms have been through multiple stars, multiple cycles of fusion and explosion, before finally coming together to form the solar system. And the cycle continues. Right now, all across the galaxy, stars are dying. Red giants are shedding their outer layers. Supernovae are exploding. Neutron stars are colliding. And with each event, the interstellar medium is being enriched with new elements. In the Orion Nebula, just 350 light-years away, new stars are forming from clouds that contain the debris of earlier stars. Some of those stars will be like the sun. Some will be red dwarfs destined to burn for trillions of years. Some will be massive and blue, destined to explode within a few million years. And around some of those stars, planets will form. Rocky planets, gas giants, ice worlds. And maybe on one of those planets in a few billion years, something will look up at the sky and wonder. It's happening right now. Not just in the Milky Way, but in every galaxy. Hundreds of billions of galaxies, each containing hundreds of billions of stars. Each star, a potential birthplace for planets, for chemistry, for complexity. The universe is not static, it's evolving. And we are part of that evolution. Here's something that might surprise you. The sun is slowly getting brighter. Not dramatically, not noticeably on human timescales, but measurably. When the sun first settled onto the main sequence 4.6 billion years ago, it was about 30% dimmer than it is today. This happens because as the sun fuses hydrogen into helium, the helium accumulates in the core, increasing the core's density. A denser core means higher pressure, which means a slightly higher fusion rate, which means more luminosity. Over the next billion years, the sun will continue to brighten. And eventually, in about 1 to 1.5 billion years, it will be bright enough that Earth's oceans will begin to evaporate. The runaway greenhouse effect will set in. Earth will become uninhabitable long before the sun becomes a red giant. Life on Earth has an expiration date. Not in the distant abstract future, but in a time frame that's comparable to how long complex life has already existed. Does that bother you? It used to bother me. The idea that everything, all of human history, all of art and science and culture, all the stories we've told and the monuments we've built will one day be erased. Not by our choices, but by the slow, inevitable brightening of the sun. But then I realized something. We are not the end of the story. We're just one chapter. If humanity survives, we'll leave Earth long before it becomes uninhabitable. We'll settle other worlds, orbit other stars. We'll carry with us the knowledge we've gathered, the art. We've created the memory of what it was like to live on a small blue planet orbiting a medium-sized yellow star. And if humanity doesn't survive, something else will arise. Maybe not on Earth, but somewhere. In some galaxy around some star, complexity will emerge again. And it will ask the same questions we've asked. Where did we come from? What are we made of? Why are we here? And the answer will be the same. You are made of stars. You are the universe looking at itself. There's a concept in astronomy called the stellar lifetime. It's the amount of time a star spends fusing hydrogen in its core, the main sequence phase. And depending on the mass of the star, that lifetime can vary by a factor of trillions. A red dwarf with 0.1 solar masses will live for 10 trillion years. An O-type giant with 50 solar masses will live for just 3 million years. The difference is staggering. But here's what's beautiful. Every star, no matter how long it lives, contributes to the cycle. The massive stars die young, but they enrich the galaxy quickly, scattering heavy elements, while the universe is still young. The small stars burn slowly, patiently, waiting for the universe to quiet down around them. Both are necessary. Both play a role. Fast and slow, bright and dim, massive and tiny. The universe needs all of them, and it needs death. Because without death, there's no rebirth. Without supernovae, there are no heavy elements. Without planetary nebulae, there's no enrichment of the interstellar medium. Without endings, there are no new beginnings. Death is not the opposite of life. It's part of life. It's what makes the cycle possible. The atoms in your left hand were probably forged in a different star than the atoms in your right hand. The iron in your blood came from a supernova. The calcium in your bones came from a different supernova. The oxygen you're breathing came from a red giant that shed its outer layers billions of years ago. You are a mixture of stars, a patchwork of different explosions, different deaths, different transformations. You are not one story. You are many stories woven together into something that can think and feel and wonder. And when you die, not you personally, but humanity or life on Earth or even the sun itself. The atoms that made you will not disappear. They'll drift into space. They'll mix with new clouds. And eventually they'll become part of something else. Another star, another planet, maybe another form of life. You are temporary, but you are also eternal. The matter that makes you has been here since the beginning, and it will be here until the end. It just keeps changing form. Stars are born from darkness. They live in light. They die in brilliance. And from their ashes, new stars are born. It's a cycle, ancient, relentless, beautiful, and we are part of it. Not observers standing outside the cycle watching it happen. We are participants. We are the cycle made conscious. Every time you look up at the stars, you're looking at your past. Those stars made you. Their deaths created the elements that became your body. Their light has traveled across space and time just to reach your eyes. And every time you breathe, every time your heart beats, every time a neuron fires in your brain, you're continuing the story. The story of matter transforming, evolving, becoming something new. The universe is 13.8 billion years old. The sun has been burning for 4.6 billion years. Complex life on Earth has existed for about 600 million years. Humanity for a few 100,000 years. Civilization for a few thousand. We are latecomers to the story, but we're here. And for this brief moment, we get to witness the cycle. We get to understand it. We get to marvel at the fact that the universe can produce something that looks back at itself and understands where it came from. That's extraordinary, maybe even miraculous in its own way. So, here's the truth told as softly as the night itself. Stars die so that you can live. Hydrogen fuses so that carbon can exist. Supernovae explode so that rocky planets can form. Red giants shed their layers so that new stars can be born. The universe is not indifferent, it's generative. It creates, it transforms, it gives. And you fragile, temporary, improbable you are, the result of billions of years of cosmic alchemy, of stars living and dying, of elements mixing and bonding, of chemistry, becoming biology, of biology, becoming consciousness. You are the universe's way of knowing itself, and for that, you are invaluable, irreplaceable. We've traveled far tonight, from the birth of stars in cold, dark clouds, to their long lives on the main sequence, to their deaths, as red giants, planetary nebulae, supernovae, neutron stars, and black holes. And finally, to their rebirth, as the matter they released drifts back into clouds and begins the cycle again. It's a long story, an old story, a story that started long before we existed and will continue long after we're gone. But for this moment, it's our story. And it's told in the only language the universe truly speaks, the language of stars. Thank you for drifting with me through these quiet hours, for listening to the story of how stars are born, how they live, how they die, and how they give themselves away so that new stars and new worlds and new life can begin. The night sky is full of endings and beginnings. Every star you see is in the middle of its own story. Some are young, just learning to burn. Some are old, nearing the end. And some have already ended their light, still traveling toward you, carrying the message of a death that happened long ago. But all of them are connected. All of them are part of the same cycle, and so are you. Sleep well, dream of starlight, and remember, you are not separate from the cosmos. You are part of it. You are stardust, awake, aware, alive. Good night.